The extraordinary thing about this workshop, above all others, is that it not only teaches how a neuron works, which can help to pass an exam, and not only how a brain works, which shows how you pass exams, but how you work, and so in a way, how society is connected together. In this workshop, the students play the part of nerve cells, or neurons. Eventually, they will join together to play a tune. To begin with, they start with something simple, the reflex arc. That's how a hand, for instance, jerks away from pain before the brain knows about it.
Go for it, let's see.
Then they learn about brains.
Your brains are full of neurons. Without those neurons, you wouldn't know anything. You wouldn't know who you are, you wouldn't know who your friends are, you wouldn't know how to think, you wouldn't know how to learn anything. It's all because of in your brain, all these connections between the neurons.
We talk about fatigue, inhibitions, thresholds, all old-fashioned words which we don't use much nowadays, but which are still applied to neurons. We get tired, our neurons are fatigued. We have excitement, while our neurons have excitation. Modern children are never inhibited, but scared, yes.
We're also going to be talking about thresholds. Thresholds are very important. You need thresholds. Who needs an alarm to wake up in the morning? Right, so you've got to have a sound that's above your threshold of sleep. Who needs 2 alarms? Okay, who needs a parent on either side going, wake up, you're late! Right, has anybody graduated to the bucket of cold water yet? How tragic is that?
On Sunday.
On Sunday?
Yeah, I slept.
That's the one you can sleep in.
No, I know. It was because we had a football match.
These boxes are the neurons. They've been cleverly connected to form a small brain or ganglion, which is going to learn a tune. Each one of the boxes has a wire going in and going out. When the signal comes in along a dendrite, it lights up the green bulb. They must then press the button to send it out along the axon. Sometimes a wire comes into the side of their box. This carries an inhibition signal. If the red light goes on, they must not pass on any signal. Right, let's get going.
You've all got your thresholds nice and high, which is good, but if we lower the threshold over here, we may be able to excite this neuron enough for it to reach action potential and press the button. She's she's not very inhibited at all. I thought she might need a bit of input from the rest of you. Do you think she ought to do this?
Yeah.
Right, so she's getting a lot of input, she's pressing the button, and does that have an effect? The neuron next to her is looking very excited. Obviously, the inhibitions are dropping there. She's going to press that button by the look of things. Ooh, press it firmly. Ooh, okay. That's happened? Yeah, all right. Give it a go. Nothing. But it sent a signal. It sent a signal, didn't it?
Yeah, it did.
Did your light go on? So you press the button. Do you hear the tune? What is it?
It's like a little...
Mary had a little lamb.
Yeah.
Okay, nursery rhyme indeed.
This is the arrangement they are in, and this is what happens to begin with. But in order to bring in the last line of the song, we have to look further into how neurons make decisions, using systems very similar to computer processors. Jonathan explains the similarities between computer processors and sets of neurons.
A thing called an AND gate, an OR gate, and a NOT gate. And it's quite simple. The AND gate is simple because if you get one signal and another signal, it passes on the signal. With the OR gate, if you get one signal or the other one's on, it passes the signal. And the NOT gate, it's quite a weird one. If you get a signal into there, it stops the signal. If you don't get a signal, it creates a signal.
So that's how computers make decisions, and in a way, that's how our brains do it. Now we can bring in the last line of the song, connect it, add a NOT gate, or an inhibitor neuron, which will stop its neighbour from firing, then 2 AND gates, that is, neurons with high thresholds which therefore need 2 stimuli to fire off. This is what the tune should look like. The inhibitor doesn't fire yet, nor the fleece neuron. The tune goes around again. This time the inhibitor will fire, the old route will be blocked, then the fleece neuron will fire off and the second part comes in. So we have been able to create a tune using just 30 neurons out of a possible 100,000 million that are normally available to us. After a few practices, we're ready for success.
Go! Yeah!
And if that sounds like someone you know practicing a tune on a musical instrument, well, now you understand what's happening in their brain. But it's not easy. As the class works together, they have to deal with the same problems as their neurons do, like attention and fatigue.
Yeah! Few miles away!
At the end of the session, we see ways in which our brain can misinterpret the signals it receives. Optical illusions give an amusing insight into the way our brains work. So the students learn about excitation and inhibition, thresholds, habituation, reaction time, attention, fatigue, learning, and memory formation. And they learn directly rather than in the abstract. If you want to find out more, stare at the centre of this swirl for a few seconds. You'll notice it's not actually swirling. And if you keep staring, in a few seconds it'll be replaced by a blue and yellow ghost. That's fatigue, neuron style.